Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started with the webinar today, I have just a couple of administrative items to cover. Since we're trying to limit our time to under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will focus on PlumeStop Liquid Activated Carbon with a technology overview on in situ containment of perfluorinated chemicals. To give us insight into this topic, we are pleased to have with us today REGENESIS Manager of Research and Development, Dr. Kristen Thoreson. Dr. Thoreson is the lead inventor of PlumeStop Liquid Activated Carbon. She heads the Chemical Research and Product Development Program at REGENESIS. Her team is focused on developing advanced technologies for the treatment of recalcitrant compounds in mixed environmental media. All right, that concludes our introduction. So now I will hand things over to Kristen to get us started.
Great. Thanks for the introduction, Dane, and thanks to everyone who's joined us today. I'm happy to have this opportunity to talk to you about our most recent technology, PlumeStop, and how it relates to the in situ containment of PFAS contamination. So where I'd like to start today is really with a brief background on the contaminants we'll be talking about today, PFAS. And I don't intend for this to be an in-depth background. I would point you to many resources that are out there that give some really nice overviews of the background, including one that I'll have a reference to in a couple slides by Dickinson and Higgins. But I would like to just point out some of the background as it relates to this technology. So what are we talking about today? Per and polyfluorinated alkyl substances that has the acronym PFAS. And this really represents a really wide, complex mixture of fluorinated compounds. I believe there's over 1,000 different compounds that fall under this classification at this point. And the two that have got the most attention to date are PFAS and PFOA, so perfluorooctanoic acid and perfluorooctane sulfonic acid. These two compounds both have a chain length of 8 carbons and are two of the most commonly detected at sites where these PFAS compounds are found. That has to do with their direct use, but also they are sometimes terminal products for some of the precursors. And they're the two that we have focused on for this presentation as well. Now these types of compounds have been used widely in many different consumer products, and that's really because they have some quite interesting properties. For example, they're water resistant, which makes them useful in things like rain jackets. They're grease resistant, which has been useful in non-stick pans, and they also do not thermally degrade or combust, which has made them useful in things like firefighting foams, which is the picture shown in the middle on the bottom, which is a hanger that had these firefighting foams released. And they've also been used in things like food containers, again, because of their grease-resistant properties. And the reason why we're talking about them and concerned is because there are many probable links to human health issues associated with these compounds. And as you may imagine, when they've been used in this many variety of consumer products, they have ended up across the environment in many different places. In groundwater, surface water, soil, and the air. And that really brings us to the difficulties of these types of compounds. Specifically, we'll be talking about when they're located in the groundwater. So I've taken some information that I saw at a presentation at Patel in 2015 by David Woodward, where he described some of the characteristics of these plumes in the groundwater. And some of the highlights that really stuck out to me at that time were the fact that these are the prime example of a large dilute plume. In many cases, they're over a mile in length. In the picture I have shown up there, it's multiple miles in length. And in fact, there are times when they can't even find the front of the plume. And the majority of those plumes, oftentimes at least 3/4, are at very low concentrations, typically less than 10 parts per billion. So we're talking about, very low-level contamination, which can often be difficult to treat across a very wide area. And because of those health issues, the EPA back in May 2016 set a revised health advisory limit for the combined concentration of PFOA and PFAS of 70 parts per trillion, or 0.07 parts per billion. So we're talking about starting with low concentrations and needing to get to even lower concentrations, which is really can be quite difficult to do with many technologies. And at this point, the tools that we have in our toolbox that have been useful for other types of contaminants that we're used to seeing have really not worked so far, and that has to do with the fact that these compounds are extremely recalcitrant. Those carbon-fluorine bonds that you saw in the compounds on the previous slide are very strong and they're hard to break down. And so these, when they get into the environment, will persist. So when we think about remediation and treatment options, again, most of what we already know or what we tend to fall back on have just not been effective. So for example, there's just no known bacteria currently that are capable of complete biodegradation. Many of the oxidation that we typically use has also not been effective at typical usage rates that we use in the environment. And there's a nice summary in this web report by Dickinson and Higgins that really goes over all of this. And so there's a lot going on in this chart. On the left-hand side, there's a number of different PFAS compounds, including PFOA and PFAS, bolded there. And along the top, there are a number of different treatment options. And basically, if it's in red, that means that those types of treatment options have not been effective to date. Whereas if they're in green, those have been fairly successful in removing these from the groundwater. So you see like nanofiltration and reverse osmosis are quite effective. However, they also tend to be quite expensive. And then if you look next to that, you see granular activated carbon and anion exchange that has good success over many of the different compounds. However, they sometimes drop off at the shorter chain species. And so, based on this, it brings up the question, well, what is being done currently? And so right now, the currently accepted method of how we can treat these is to use a pump and treat system where we pump the water through a granular activated carbon bed. And that has been quite successful to date at cleaning up the groundwater. And so it brings up the next question, and this is really what we're trying to focus on in this presentation, is if we can use granular activated carbon ex situ, can we be using activated carbon in situ as well? And that's where we're heading here today. And before I jump into too many more details, I would just like to kind of preface this idea that when we're talking about using activated carbon ex situ versus in situ, we are looking at some different types of parameters, really looking at different types of flux rates that are going through those. So in a pump and treat system, you're obviously under pumping conditions, which means you have high flow rates, high mass flux rates, and a general shorter residence time in those beds. Whereas if we can use activated carbon in situ, then we're looking at using the natural flow rate of groundwater and an overall lower mass flux rate and a longer residence time or interaction with that activated carbon. So I just wanted to kind of point that out at this point, and then we'll go from there. So a few years ago, we set out to develop a new in situ technology, and when we were in that development stage, in the R&D stage, which again is where I come from, so this is the part that I enjoy but also can be the challenge, is we really wanted to develop something that had a few key functions. Namely, its ability to distribute in the subsurface to make sure that we can get contact with contaminants, and also ideally not have to require too many injection points or have a need for fracking, and also something that can absorb quickly and accelerate biodegradation. Of course, this assumes that there is a biodegradation pathway available, which there is currently not for PFAS, so I'm not going to go into that part of it at all today. And what we came up with was PlumeStop Liquid Activated Carbon. So you see in the picture, it really looks like a black ink. And it is based on colloidal activated carbon, meaning activated carbon on the size of 1 to 2 microns. And then there's some additional additives, some polymers, and some other molecular additives that allow it to distribute in the subsurface. And since it is based on activated carbon, the contaminants that we can treat with this, and what we have been treating since its launch a few years ago, is primarily chlorinated solvents like your PCE, TCE, as well as petroleum hydrocarbons. But really anything that has an affinity for activated carbon is a place where PlumeStop can be used. So that includes PFAS, since we know that currently granular activated carbon is already being used to clean these up in the pump and treat systems. So the outline for the remainder of the talk is what I'd like to go through is the ability of PlumeStop to distribute in the subsurface. And this is really a key part, because if we cannot get PlumeStop into the subsurface and have it distribute, it's not going to be successful. So I'd like to show some examples of how we get this into the ground and what we expect of it. And then we'll move into more specific, the adsorption of PFAS, how long may we expect it to last. And then finally we'll end up with some in situ containment strategies where we believe PlumeStop could be used in some of these large plumes. So a good place to start when we're talking about the distribution is this simple column test that we've ran in our lab. And so these are soil columns that are mostly sandy, but they're not clean sands. They do have silt and clay within them. And they're operated completely by gravity feed. So at the bottom you can't see it, but there's a little stopcock at the bottom that can be opened, allowing it to drain. And for this demonstration, we have liquid activated carbon on the left and like a commodity powdered activated carbon on the right. And in both cases they have the same total amount of carbon as a slurry, which will be applied to the column and then flushed with a few pore volumes of clean water afterwards. So I'll show you this time lapse of what this looks like. You can see that the liquid activated carbon is able to readily distribute through the column as opposed to the powdered activated carbon, which gets essentially filtered out within the top half or 1 inch or so of the column. And again, this was flushed with clean water at the end. So I'd also like to make sure to point out that you can see a staining of the soil after these columns have been flushed in the liquid activated carbon. And that is really important because the formulation of PlumeStop allows it to distribute within the subsurface, but we obviously do not want it to distribute forever because then you just have a plume of PlumeStop moving, which wouldn't actually help us at all. So there is an affinity between PlumeStop and the soil surface, which allows it to actually deposit. We've called it painting the subsurface with activated carbon, and that is that staining that you see. So if we would take a closer look at what that actually looks like on like the molecular level here, these are some scanning electron microscopy images. On the left is a clean sand, and on the right is a sand that has PlumeStop deposited on it. And so you can see there that that scale is about 50 microns, and so we're looking at those colloidal particles of PlumeStop deposited onto the sand in that picture on the right. So when we talk about the ability for PlumeStop to distribute, we get many questions regarding how does it distribute in low permeability zones, how can it deal with contamination in clays, and an injection radius of influence, which are all very good questions. And I think to answer these, it's important to take a step back and think about, well, where are we trying to get PlumeStop within the aquifer in order to be able to fully address all the contamination? So if we look at this illustration of an aquifer flux zone, you can see that in like most sites there's some heterogeneity. So there's going to be some higher permeability zones, which I like to think of as freeways. This is where the water's moving, and then there's also lower permeability zones. I think of them more like parking lots where the water is not moving through as much. So now when we talk about contaminants transporting through the aquifer, how are we getting these 1, 2, 3, 4 mile plumes? They're obviously taking the freeways. They are moving through those higher permeability zones. And the way that you get contaminants into the lower permeability zones is through forward diffusion as they're traveling in those higher permeability zones. So there's going to be forward diffusion where the contaminants move into the clays, and that acts as residual storage over the long term. Now we know when we go out and apply PlumeStop, the places where it's going to be the easiest and the most, where we're going to get the best distribution is in those higher permeability zones. We apply PlumeStop most often with direct push or through injection wells under low pressure to avoid fracking. And so we're going to really coat those high permeability zones with PlumeStop. And as you saw in the pictures before, we leave that coating, that painting of PlumeStop there, which allows us to address the the contaminants that are present in those high permeability zones. But then also, it's set up nicely to catch any kind of back diffusion that's going to happen as the contaminants move out of the low perm zones and back into the high perm zones by having that PlumeStop permanently adhered there. And so really when we think about the distance and radius progressed, it's going to depend on the volume, it's going to depend on those high permeability zones as to exactly how far we get. And we do a lot of upfront work prior to doing an injection to really try and identify those zones and to understand where we're injecting the PlumeStop so we can have a good feel for where and how far that PlumeStop is going to go. I'll touch on this briefly in another couple slides as well, just to get a little bit more into how far PlumeStop does travel. So here's a soil core that was taken at a PlumeStop site after PlumeStop was applied. And so you can get this kind of feel very nicely. You see the low perm zone where there looks like a fairly tight clay, and you don't see PlumeStop there. However, there's a higher permeability zone that looks like it's probably a little more sandy, and that's where the PlumeStop is applied. So this gives you an idea of the field, and I'd like to take a moment to go into this just a little bit further by looking at a laboratory study that we've been doing over the past year. This is actually a collaboration with Tom Sale at Colorado State University and Kevin Saylor at CDM Smith, where we use these laboratory tanks to really simulate back diffusion and to simulate these high and low permeability zones. So you can see in that picture there's a tank that has all these stripes, and those different stripes are alternating layers of low and high permeability soils. And it's operated in upward flow, and the objectives for this study for us, we were looking at TCE and the transport back diffusion and all that, which doesn't apply to this talk. However, it does allow us to give an example of how PlumeStop travels through a situation like this. So in this study, we applied PlumeStop with about 1 to 1.5 pore volumes, and then followed with clear water flushing. And so the results of that, you can see in this picture, is very good distribution of PlumeStop through those high permeable zones, but also some penetration into the low permeable zones, which we were quite pleased with, because it's obviously always nice to get some contact in those low perm zones where there is contaminant stored. Here's another picture when we were dismantling these tanks. So you can really get a feel that there's fairly uniform distribution across both the high and low perm zones. And the picture on the left shows that coloration does go all the way through. It's not just on the surface like a kind of a glass effect. It does go all the way into those low perm zones where it had contact. So if we relate it back to our first illustration, you really get a nice feel for these where we're trying to put PlumeStop, and we actually do see a little extra penetration into low K zones, but we're really trying to target those high K zones because we know that's where we're going to stop the contaminant flux and also be able to capture any back diffusion. So one final point on the ability of PlumeStop to distribute, as I mentioned earlier, we wanted to make sure that we're not going to see any type of plugging or self-clogging if we keep putting PlumeStop into these zones to see really how far could we expect it to go. So we set up a 16-foot column in our warehouse and filled it with fine to medium sand, operated an upflow, so you can see a little pump on the bottom, and we pumped water, and then eventually PlumeStop up through this column. And in the end, we put about 5.5 pore volumes of PlumeStop through, and then flushed it with 9 more pore volumes of clear water. And all this was done at low pressures. And the brief highlight of this is just to demonstrate that we saw a nice distribution as it flowed up the column. So you can see the 4-foot mark, you have a nice front coming up, and then as it approached the end of the column, and we did see it completely go through the entire column, and we had some coming out. So that actually suggests that it went 16 feet, but if it had been a longer column, it would have been able to transport even farther in this case. So in these high perm zones, we do expect to have excellent transport of PlumeStop to be able to, put our injection points a little bit farther apart and still get good distribution. So now I'd like to move into PlumeStop with PFAS, and specifically PFAS absorption, and how long we might expect it to last. So anytime we're going to try and identify the dose response for PlumeStop with a contaminant that we're interested in, we'll go into the lab and measure the isotherm, which is really a partitioning equilibrium between how much of the contaminant ends up on the sorbent, on the activated carbon, and how much is left in solution. And so we've done that for PFOA and PFAS and some of the other PFAS. And, unless you're really used to looking at isotherms, these are a little bit hard to understand as to what this means. Are these good? Are these bad? And so it brings up the question of, is there another way we can interpret these isotherms? And so a direction we've been working and continue to work on is the idea of integrating PlumeStop within fate and transport models. And the idea here would be to use those isotherm parameters that we measure in the lab and incorporate them into models in order to allow us to predict the longevity of PlumeStop and also to optimize the dose to meet desired longevity of what your site might be requiring. And so we have been collaborating with Professor Arturo Keller at UC Santa Barbara to do just that, to kick this kind of idea off. And so in this case, we've incorporated PlumeStop into the BioChlor model in order to look at this. And so I think the best way to go through this is to look at an example. So in one simulated plume scenario, we'll look at a 50 parts per billion PFOA plume, which is really the source on that diagram. And that will have moving at about 120 feet per year. And we'll look at the model over the course of about 8 years. And then in the second scenario, we'll be able to add in a PlumeStop treatment, basically add in a PlumeStop barrier and see how that changes the transport of this plume. So in this scenario, we'll look at a 25-foot PlumeStop barrier at a very typical field dose. And then we'll be monitoring the downgradient concentration, again, over those 8 years, looking for how long we can keep the concentrations below those health advisory limits that the EPA recently set. And again, the key part here is we're assuming only sorption. As I mentioned before, there's really not many options at all for any kind of degradation. So when we're talking about using PlumeStop, we are talking about containing the plume. We're not talking about destroying it. So this is a sorption-only process. So if we look at the results of this model output, so the first scenario is when you just have the natural flow of the plume over those 8 years. So you can see that after that time frame, the plume will have extended at least 1,000 feet at concentrations above the EPA health advisory limit. Whereas when we put in a PlumeStop barrier, we're now able to contain that plume over those 8 years without having any concentrations above the 70 parts per trillion eluting from the barrier over that time frame. So a very stark difference. You see, the kind of classic example of a plume contained by installing a PlumeStop barrier. Now, of course, this is one scenario, and there are going to be many factors that will impact that longevity. So we're really talking about mass flux and how much flux is going to come through that barrier. So we need to look or think about seepage velocity. So as you can imagine, if that plume was moving much faster the breakthrough time would be shorter. We wouldn't have seen the 8-year time frame. We might see something less than that. But then at the same time, if it was moving a little bit slower than that, we'd expect to have longer containment. Similarly, the contaminant concentration is going to play a large role. So again, if it's at a higher concentration, that will break through more quickly than if it is at a lower concentration. It's also very important to know and understand whether contaminants are present. There is competition for these sites on activated carbon, and so that's something we do a lot to take into consideration. So if there are other, if it's, in many cases, it's not going to necessarily be a single component plume, so we're going to have to take into account anything else that's there, and then think about how those are going to compete, and that's going to influence the longevity of these barriers. And also not even just contaminants, but anything else that could possibly compete for those activated carbon sites, like dissolved organic matter. And then, of course, the PlumeStop dose. So that's something we can play with to try and get more or less a longer time frame by increasing the PlumeStop dose as necessary. And so another way to really describe all of this, in perhaps a more familiar term, is really thinking about a retardation factor. In essence, that's really what we're doing here. We are engineering the aquifer retardation factor by being able to paint the subsurface with activated carbon. Activated carbon has much higher absorption capacity than any kind of natural FOC, so we're really bumping that up to something that's going to relate to a much higher retardation factor than what you typically observe. So taking a step back, just thinking about what exactly that retardation factor means. It's how fast the contaminant is moving relative to groundwater. So when you have an RF of 1, you have no retardation, so the contaminant's moving at the same rate as groundwater. If it's 2, it's moving at half the rate, and if it's at 10, it's moving at 1/10 the rate of the groundwater. So some of the typical retardation factors that might be observed for VOCs and also from PFAS and PFOA are somewhere in the range of 1 to 20. Again, with normal FOC type values that you would encounter in the subsurface. So now when we talk about using PlumeStop, again at the same kind of dose that we used in that model scenario previously, we're now talking about changing the retardation factor of, for example, PFOA by orders of magnitude. And again, that depends on what the concentration of that PFOA plume is. And it's a similar or even a slightly improved case for PFAS, as it has a little bit more stronger affinity for activated carbon. As we saw early on, in many cases, these plumes are on the lower concentration range, so we're talking about changing the retardation factor by the 3-4 orders of magnitude or more when we're able to apply PlumeStop in the subsurface. So finally, I'd like to end with a couple ideas of where PlumeStop can be used on these large plumes, some containment strategies. So we'll take you through a few illustrations of this. The first one is really the model that we already looked at, and that's just using a single barrier to cut off the plume, with the idea there to contain the plume and limit its expansion. This comes in handy if you're trying to keep the plume from moving on to a neighboring property or protecting a sensitive receptor like a river or something like that, as it's shown in the picture. And the idea here is if you know the total mass that's upgrading of that, you could essentially dose that barrier appropriately in order to contain that plume so that now it's contained completely within that barrier rather than across that entire zone. A similar strategy is now just using a sequence of barriers. So this has the possibility of addressing a larger area of the plume. And again, it allows you to potentially contain that plume in multiple short areas, short barriers, rather than having it across that entire site at this point. In a third strategy, it's kind of a unique idea. It's more of a emergency response or preemptive type controls, that if there's a place where there might be a spill, or even if a spill just happened, you can potentially use PlumeStop here to contain it so it doesn't even develop a plume. So in this case, you can see here's your spill, and as it would now typically start to move down and create a plume, it's now contained within that barrier that you put up around it. And then the fourth strategy here, we're thinking about localized receptor protection. So again, these plumes are usually quite large, so it may not be feasible to use this in a wide area of the plume. However, if there's a certain neighborhood or a well or something like that, you can actually do just the opposite of what we just described. You can actually surround whatever that is you're trying to protect, and essentially you're making a Brita filter. This would allow you to put PlumeStop in around there so that if you're extracting water out of that well, you have an interim procedure to help clean up that well and prevent those contaminants from getting in that receptor. And then again, as I mentioned, these plumes are usually quite large, so that you can start to pick off little portions or certain areas that really need to be addressed immediately, rather than thinking about the entire thing by using something like PlumeStop. So just to review the technology benefits where PlumeStop can help manage PFAS plumes, is that we really have the ability to turn the subsurface into an activated carbon filter. And this comes into play because it's injectable. You can put it at wide centers and at depth. And as we went through, it really allows you to engineer the retardation factor. And that all has to do with this ability to inject activated carbon, have an injectable form of activated carbon. And is what this gives you at the end of the day is a passive plume control and containment. So by putting in a passive barrier, it leads to perhaps an avoidance or even a decrease in some of the ex situ pump and treat systems and the expenses associated with that. But really, a key part of it is it prevents the expansion of the problem without interrupting the groundwater flow. So, keeping it to a smaller problem for now by putting up fences around it. And then the final point I'd like to end with is that, when we use PlumeStop for other contaminants, we often pair it with some kind of destruction technology like, an enhanced reductive dechlorination by adding an electron donor. And so obviously there's a lot of people working hard right now to try and come up with some destructive technologies for these PFAS compounds. And so there's certainly potential to contain these plumes within a PlumeStop barrier and then go back down the road when a destructive technology is developed and pair it with that and go and be able to kind of clean up those barriers over time. And so with that, I'd like to close, and hopefully we have some time for some questions.
Yeah, definitely. Thank you, Kristen. That does conclude the formal section of our presentation. At this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a few reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you will receive a link to the recording as soon as it is available. All right, so let's circle back to the questions. If we are unable to answer your question, we will follow up with you after the webinar. All right, so Kristen, the first question here is, given that PlumeStop was developed to disperse in the aquifer, what's to stop it from remobilizing over time and increasing concentrations seen in production wells? Has this been tested to see if there are any soil types that it does not adhere to?
Okay, that's a good question. So as we saw in that soil column that we looked at early on, and we saw that painting of the aquifer, so that has to do with all those additives that are present within the formulation. And as the PlumeStop adheres, that is a permanent fixture, and over time the other additives will wash away or degrade, which means that the mechanism for any movement of the PlumeStop is now going to be removed over time. And so there really is no possible way for those particles to remobilize at that time without any kind of basically their cars have been taken away from them at that point, and they will agglomerate and not be able to move any further. So we don't see that kind of remobilization. And it is important to know that the amount and the extent of which we have PlumeStop deposit is going to depend on the soil type. And so we know that the more clay and silt that's present, the more PlumeStop will adhere to it as opposed to a clean sand. So that's something that we take into account, and it's important for us to know as far as understanding how far we expect it to go. So there is not any soil type that it will not adhere to. It's just a matter of how much it'll adhere.
All right, great, thank you. So next question here is it possible to reach the low levels required by regulatory cleanup levels?
Yeah, so that's an important question, obviously. We need to make sure that's possible. And I think, we have evidence because granular activated carbon is already used ex situ. And the good news about activated carbon is that it actually works a little bit better at lower concentrations. The way the isotherms work is that they actually improve at lower concentrations. That's where they get better, which is in opposition to most technologies. Usually you lose efficiency at lower concentrations. So this is a good part about activated carbon. But in the end, yes, we can reach those regulatory cleanup levels with PlumeStop as well.
All right, thank you. So the next question here is, can there be re-injection after the PlumeStop is spent?
Yeah, so that's an important one when we're thinking about PFAS, since we don't have a destructive pathway right now, and so we're talking only about sorption, which means that there is likely a time point when the capacity will be filled up. And at that point, there is no issue at all with going back and re-injecting more PlumeStop, either into the same wells or same general area through direct push where it had been applied previously. We will see an additional coating go up in that same area. We might see a little bit more transport slightly farther down gradient, but in general, we'll end up applying an additional layer of PlumeStop in that same area. And we also have some means that we're working on right now to really control where the PlumeStop is going, so we can try and make sure we get a nice kind of thick dose where we need it. If there happens to be a soil type where we don't see as much deposition as we'd like, we do have a means for increasing that as necessary.
Okay. Next question here is, what analyses should be run to determine if PlumeStop is going to work, including soil and/or groundwater chemistry?
Okay, that's always a good question when we're thinking about in situ technologies. And I think there's two parts actually to this question. And one is first just like getting PlumeStop into the ground. Is there anything that we look for? And we will tend to analyze for total dissolved solids and cation concentrations, because that can affect how far we expect it to go. However, the good news is that most concentrations that you encounter in aquifers are really not going to have any impact there, but it's something we will check prior to injection to make sure we're not going to run into anything that might limit its transport. But generally, PlumeStop can be used in wide-ranging redox, DO, ORP types. It's really robust in that nature. The second part, I think I alluded to a little bit, is really understanding everything that's present in that aquifer, which means knowing all the contaminants or anything that might have, TOC, anything that might have a potential to absorb to carbon, because we can't preferentially only absorb the contaminants we're interested in. So we need to really know the full picture at every site so that we know how to design for it and make sure we get enough PlumeStop in to capture the contaminants we are interested in. So even if there are contaminants that maybe aren't ones we're looking for, we need to know about those as well to get the proper dose installed.
All right, great. Okay, the next question here is, what about the shorter chain length PFASs? granular activated carbon is known to be largely ineffective for shorter chain lengths.
Yeah, so that, is, when you think about granular activated carbon, it is going to have a stronger affinity for those longer chain length PFAS compounds like PFOA and PFAS, but there certainly are shorter chain length ones present as well, and the affinity does drop off. And so, what has been observed with granular activated carbon is a similar trend we observed with PlumeStop. I would point back to one of the earlier slides that I talked about, is that when we're putting PlumeStop in the ground and we're using the natural flow rates, that total flux it's going through is going to be whatever that natural flow rate is. And so if we know all these isotherms and we know how they're all going to interact, it's something we can design for. It may require multiple barriers in that case to get everything, including those shorter chains which have less affinity. But the trends are the same as far as what has been observed with other activated carbons.
All right, thanks very much, Kristen. That will be the end of our chat questions. If we did not get to your question, someone will be following up with you. If you need immediate assistance with a remediation solution from REGENESIS, please visit regenesis.com to find your local technical representative, and they will be happy to speak with you. Thanks again to our presenter, Dr. Kristen Thoreson, and thanks to everyone who could join us. Have a great day.